Welcome everyone. So this is our 67th live stream geometry. We have 3 people here with us now from all over the world. And today I'm going to take problems, some of them from a contest created by former participant I3435. So he wrote a book and I've taken a lot of problems from that book in past sessions, but this time I'm going to take some problems from a mock geometry Olympiad contest that he created. So I think maybe 3 of the problems are from that contest. I took another 2 from the Mexican Geometry Olympiad, and one of the problems is from one of the participants on this session, Stefan Sebez. So we will see how that goes. If you'd like to join sessions in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video, and the sessions are on Sundays at 8 a.m. US Central Time. All right, so with that, I will get started and share my screen. So here's the first problem I chose. So we have a triangle ABC, and D is the foot of the altitude. And then we take the midpoints of BD and CD. All right, so let's draw that altitude. This is point D. And then we take the midpoints of BD and CD. That's going to be E and F. And O and Q are the circumcenters of ABF and ACE. It's an interesting configuration. And P is the intersection of OE and QF. Okay, so let's draw those centers. It's going to be O and Q. So this is it almost looks like OQ is parallel to BC. Not sure if that's obvious. Is that true?
Yeah, that's obvious from the radical axis.
Okay. Yeah. Yeah, that is obvious because AD passes through this point. So let P be the intersection of OE and QF. We want to show that PB equals PC. Okay. Let me hide these lines. Oh, whoops, that's not right. There we go. And we can draw this. Is O the midpoint of PE? Yeah, I think it might be. Let's check. Yeah, it sure looks like it. So if OQ we know is parallel, yeah, so it looks like, yeah, O is the midpoint of PE, and similarly Q is the midpoint of PF. Yeah, because, so just to clarify, like
Can you draw the
why,
other foot,
can I draw what?
other foot of the perpendiculars?
Oh, yeah. Oops, sorry. G, whoops. I want to make this H. And then that will be J. And I see someone's written something in the comments, so give me just a moment. Okay. Maybe introduce the midpoint of BC. Okay, I can do that. So yeah, we have BD times DF. So yeah, if we let AD meet one of the circles at G prime and the other at G double prime, then by power of a point, we'd have BG prime as DG double prime. And so, yeah, if KF equals BE, then O is the midpoint of PE. Interesting. But we can prove that K, like it's not hard to prove that KF equals BE, right? Yeah. So how does it follow that O is the midpoint of PE? I don't know, is it obvious that once we know KF equals BE, then O is the midpoint of PE? Is that obvious or? Hmm. And is PK perpendicular to B? Oh, well, basically we want to show that PK is perpendicular to. Yeah, if we can show that PK is perpendicular to EF, that solves the problem. So I think there's a typo in the last thing you put. KE or KF equals ED equals BE. KE equals FC. Yes. That proves that OE equals OK and QK equals QF. And we also know that OQ is parallel to BC. Yeah, so I think maybe that might do it, because we would have OE equals OK and QK equals QF. And we also know that OQ, we're not done. Okay. Oh, we are. Yeah, because if this is parallel, right? Oh, but OQ is parallel to BC. We know that, right? Because OQ is perpendicular to AG.
It fixes point K. Thus, we can finish from there, but I'm not sure how to finish by using OQ is parallel to BC.
Well, we know that EK plus KF is twice OQ, or do we know that? Yeah, because basically if you drop perpendiculars from O and Q to E, like the perpendicular from O would go to the midpoint of EK, the perpendicular from Q would go to the midpoint of KF. So basically OQ is half of EF. And so that proves that O is the midpoint of PE and Q is the midpoint of PF. And then since triangle OPQ is congruent to OQK, like PK is perpendicular to EF. So I think that finishes the problem. Yes. All right, so I'm going to type it up and then we can move on to Stefan's problem. So first, the way I'm going to do it is I'm going to say, let AD meet the circumcircle of ABF at G. And then I'm going to use power of a point. So we have AD times DG is equal to BD times BF is equal to 2 ED times DF, which is equal to ED times DC. And so that means that AEGC is cyclic. And okay, so then we know that that circle exists. Then from there, it's not hard to show that, yeah, BE is equal to KF. So I'm going to just copy what we had in the chat, or what Serdar put. So just because I'm lazy. So if KF is BC minus DC over 2, which is equal to ED. So once we know that, well, yeah. First, I'll write that OQ is perpendicular to AG. So OQ is parallel to BC. So okay, we have this. So yeah, I'll just say similarly KD equals FC, or I'm sorry, KE equals FC. So by symmetry, OE equals OK and OQK equals QF. All right. And then, yeah, I'm not really sure how to word this, but basically, if we, do I have to, is there a way to say this without having to draw perpendiculars from O and Q? Because these two imply together that, I'll just say, combining the above with OQ parallel to BC, we have that EF is twice OQ. I just don't feel like saying drop perpendiculars from O and Q. OQ is the angle bisector of KOP. Yeah, that's yeah. So I'm just gonna finish writing what Geo King wrote. Right, and so once we know this, then we know that PK, oh, I didn't even define K. So I'll do it at the beginning of the question. Here, I need a $sign here. Let K be the midpoint of BC. All right. And so PK is perpendicular to BC, implies PB equals PC. All right. And we'll move on to the next one. It's a nice solution. So here's a problem that Stefan created. So we have BE and CF are altitudes of a triangle, and then M is a point, so that AEMF is a parallelogram. All right. Okay. So you have BE, maybe like this. EF, it's going to be orthocenter, and I will do it this way. So I'll take the midpoint of EF and I'll reflect A across it. So this is M. I can hide D now. And then BM and CM intersect AC and AB at P and Q. So this is P and this is Q. Yeah, I'll ask Stefan, but I'm curious whether he found this problem just by playing around with stuff, or if he was working on another problem and then figured this one out from that. Okay, so we won't.
I made this problem by solving it. Like, it wasn't actually just messing around, but it was the solution in the and the statement was like in the same time.
Ah, okay, interesting.
That is unusual. Most of the time it is that I just mess around and find something, but this wasn't the case.
That's cool. Interesting. All right. So it might be easiest here to define this point and then show that AGQM is cyclic, or AGQP is cyclic. Interesting. So it's like at the same time you found the problem. Yes, I can draw the intersection of AM and EF. Maybe I'll draw the line EF just. Are Q, H, and P collinear? That's a good question. No. Should I let EF intersect BC? We don't know if we'll need that, but I'm not going to draw it just yet. If we can figure out why we might need it, we'll draw it back in. All right.
You draw segment EF.
Yes. Hold on just a second. So this altitude, this altitude. So yeah, AFME or AEMF is a parallelogram. I is going to be the center of that. So we know that I think GH passes through the midpoint of BC, right? And also the antipode of A. So maybe it's worth drawing that. I don't know if we'll end up using it, but so maybe we could solve this with like spiral similarities. So we want to show AGQP is cyclic. That's the same as saying that GQP is similar to GBC. Maybe we could even use the isogonal line limit somehow. Or the power ratio lemma. Let's see. So actually, I kind of like the power ratio lemma. So we want to show that so the power of Q with respect to this circle is AQ times BQ. And if you take the power with respect to this circle, it's AQ times QF. Basically, we want to show that BQ over QF is CP over PE. Oh, that's what Geo King said. Sorry, Geo King already said that. Okay. Yeah, so that seems like a good strategy. Maybe we could use the gliding principle somehow. Let's see. So this is equal to angle A, and this is also equal to angle A. So if we extend this, I wonder if Menelaus might work here, because basically if we draw these two, then FBL is similar to ECN. Sorry. So we want to show that FQ over QB is EP over PC. What if we used Menelaus? So we have CL over CB times BQ over QF times FM over ML is equal to 1. CL over CB is the same as AF over AB. And FM over ML is the same as that's either AE over ML or that's AP over PC. So yeah, we have AE over ML. Is there anything we could do with that? I think we're close here. So we have AF over AB and FM over ML.
Aren't we done?
What?
If we project through M, F goes to L, E goes to N, P goes to B, and C goes to C from right hand side, and the left hand side is the same, so the ratios are the same.
Okay. So you take FQB and you project through FQB and A, or FQB and
FQV and E.
And E. Okay.
So the line parallel to AB.
Okay. So yeah, there's a pretty quick projected solution. Okay. So I guess I'll just kind of write the proof in reverse, because and I'll make the power ratio lemma the last step. So we have FBQ comma and then the point at infinity. So basically projecting through M onto BC. All right. Let's make this another line. And so that would be L LBCN. Okay. And then similarly, ECP infinity. Not sure if I wrote this the best way, but so let's see, we're projecting. So that would be NCBL. So, and if we rearrange, that's the same as LBCN, because you can switch each of the two and switch the order. Okay. So, yeah. So this means that FQ over QB is equal to EP over PC. Then here we can apply the power ratio lemma. So let's see. So we have, we take the ratio of the powers. So I'll rewrite this as FQ times AQ. QB times AQ is equal to EP EP times AP I was thinking about using Isogonal line lemma because I feel like whenever I see that parallelogram what is it, AFME, like I feel like there's a lot of times the Isogonal line lemma is used. So this is
I used the Isogonal line lemma in my solution, actually.
Or you did. You used it, yeah.
To get the ratio of sides and then the power ratio lemma I also used. So that part is the same, but
okay.
the first part is different.
Interesting. So
I can tell how I did it after you write the solution.
All right. By the power ratio lemma. Then we have AGQP is cyclic. I should define G in the beginning. AGQP
Actually,
is.
It's just spiral similarity.
Oh, once you have these two? Oh, yeah.
Yeah.
Because it means that. Yeah, also.
Incenter takes FE to QP and QP to BC.
Yeah, no, you're right. It's just a spiral similarity. So I'll just say alternatively, we can use just use a spiral similarity about G. All right. So let AFE meet ABC at G. G. Okay. And okay, so that means that the circumcircles of those three concur. have a common point different from A. Or yeah, coaxial, that's the word for it. Okay. So we used the isogonal line lemma to get the ratio of the sides.
Yeah. So the triangle BHC is where we will use the isogonal line lemma. BHC.
Okay.
Here, HM and HA are actually isogonal.
I feel like I did a problem like that once. So HM and HA are isogonal.
Yeah, that can be proven not very hard. For example, you can observe that H is the orthocenter of EFM, and then MH is perpendicular to EF, and that would get the result pretty much very fast.
Okay.
And then when we have that those are isogonal, then we can use the isogonal line lemma and see that Q, which is the intersection of AB and CM, that it is so HQ is isogonal to HP, because that's how isogonal line lemma works. Those two are the intersection points of interest. So we would have that BHQ, that angle, is CHP.
I see. And then because these triangles are similar, BHF and CHE, then those ratios are the same.
Yeah.
And then you can finish with spiral similarity or power ratio lemma.
Yeah,
so
I
nice.
originally did with power ratio lemma, but today I saw that we can do also spiral similarity.
Yeah. And basically the idea that is yeah, GFB we know is similar to GEC. So if these points are in the same ratio, BQ over QF and CP over PE, then GFQ has to be similar to GEP. So by a spiral similarity, a GQP is cyclic. That's pretty nice. I don't know how, I never realized that like you could basically prove one using the other.
That is that's actually really interesting. Also, this is like just a, let's say, a special case. So basically, this coaxiality would work for any point on line HM. It was just that you would need to see that HM is isogonal to HA. So
okay, so for any point on the ray HM,
the line, it doesn't have to be on the ray.
Okay, the whole line. Yeah, then you define P and Q like that, and then that would be cyclic. That's kind of interesting. Yeah, that's an interesting property. All right, thanks for proposing the problem. Okay, so this one I think might be a little harder. So this was from a mock GEO contest by I3435. A lot of these problems were short, but I don't think that necessarily means that they were that easy. So let's draw the A mixed linear incircle. I wish there was a fast way to draw it, but yeah, I'll draw the incircle and do it the usual way. Oh, you solved this one? Okay. So yeah, Serdar, if you did this contest, okay, let's see if we can solve it without Menelaus. So let I be the center. And it's tangent to, okay, the incircle is tangent at D, but then we need to draw the mixed linear. So, whoops. Let me draw AI, then I'm going to draw the perpendicular to AI. and it intersects AB and AC at those 2 points. So really, it meets AB. I mean, really, we could just say this is B1, right? I don't even think we really need to show the mixed linear in circle. It might help, but that's B1. And we want to show that B1D. Okay, so really we want to draw this whole ray right here. Whoops. So let me draw the ray. So the line through C perpendicular to that. So basically parallel to B1F, right? So we try to figure out where B1D meets that. And we're saying it meets it on the A median. So we could take the midpoint of BC. Let's call it M. We want to show that A, M, and E are collinear.
You change F to some other letter and name other tangency points as E and F.
Okay. Hold on one sec. Actually, you know what? Let me do this. Okay. So call this L, and we'll call the other tangency points E and F. B1D. All right.
Intersect HC with AB.
Okay. Let me. See if that fits on the, yeah, we got right. Waiting for this to go away. There we go.
Take the intersection point of AI with BC also.
Okay. Just a second.
Then we can project the cross ratio BC and M.
Okay.
So let us firstly think of what that cross ratio is. So BC and M, that is equal to Bn over Nc over Bm over Mc. So that is Bn over Nc because M is the midpoint. And Bn over Nc is AB over AC.
Yeah.
So we have a really easy expression for that cross ratio. So if we project, we will need to prove that M projects to L to prove that those are collinear.
Okay.
So we just need to prove that cross ratio JCHL that is equal to AB over AC. But H is also the
midpoint.
The midpoint. So we just have to prove, I think, that HL over LC is AB over AC.
Interesting. Okay, so yeah, we want to show HL over LC is AB over AC. I don't think B1L is parallel to AC, right? Maybe it is. Sorry. Seems very unlikely that that would be true, but yeah, that's not true. Okay, so HL over LC, we want to see if we can figure that out. Maybe we could project through D. Like what if we project HLC through D onto AB? So L goes to B1, C goes to B. C, where does H? I would be very surprised if H went to F. Oh, I think, let's see. Yeah, it looks like H, D, and F are collinear. So that would probably help.
Oh, that is actually just the iron lemma.
Oh, it's the Iran lemma that H, D, and F are collinear. Yeah.
Yeah, because of the 90-degree angle.
Okay. So yeah, we could try projecting HLC through D, and we get B, B1F, and do we want to do HLC and J? Or
I don't know if we can project 3 points. So no, we can't project 3 points. Just so we need to have cross ratio JCHL.
so yeah, JCHL would project to these four. And then what? And then these four, if you just all take the parallels to B1K, they project to EK, C. So yeah, let's draw the parallel through B to B1K. So basically, we just need to show that.
I don't think that helps since it is just symmetric.
Exactly. Yeah, it's just symmetric.
But I think that all of these lengths should be computable. Like,
yeah.
So if we can just compute that cross ratio is equal to that, then we're done.
Yeah, it seems like it would just be a calculation. I wonder if there's a way without having to do the calculation, but yeah, I'm not sure. Because, well, let's see, because IFB1 is similar to AIB1.
Can you draw HMK?
HM.
HMK.
Okay. Oh, did you want to see if they're collinear?
Okay, I missed K as the midpoint of AC. Okay, it's not.
Oh. No, I don't think K is the midpoint of AC.
Yeah, it's not. I know. If it was the midpoint, they would be collinear.
Okay. So yeah, everything is computable. So yeah, we could finish this problem with a calculation. But so yeah, BJ is AC minus AB. And yeah, I agree, everything's computable. Is there a way? I still kind of like drawing this parallel line just because I feel, well, okay, so this is AB, AJ is AC. So basically we wanted to show The cross ratio of these points is AB over AJ. Yeah, we could do a calculation. I just wonder if there's a better way. So, because we have so many similar triangles, right? AIF, AIB, AHJ. One sec, guys, I'll be right back. All right, thanks for waiting. It's like blue
Name the
Hawaii.
intersection of B1L and AH.
B1L and AH. This point?
Yeah.
We'll call it P. Yeah, how can we simplify this cross ratio without having to do a calculation? Is there a way? That is the question. So what we could do, let EF intersect AI at a point. So basically the cross ratio FB1BJ, if we take perpendiculars onto AI, that's O, sorry, it drives me crazy seeing that O. That would be QIH and then whatever this point would be. I don't know if that would help. Or just make things harder. This Q is, we'll just erase that for now. Yeah, we just need to project through one more thing. Yeah, what if we projected these 4 points through I? Because yeah, we want to use that BI is perpendicular to AI, right? Let me check something. I wonder if, what's the bisector of angle Fij? Okay, never mind. Yeah, it's kind of like, yeah, we're just trying to solve this without using a calculation, or a long calculation, I guess. What we could also do, what if we took these 4 points F, B1, B, D, and we reflected across IB? So
Can you draw ID?
yeah, one sec. Sorry. So F goes to D. B1 would go to O. And J would go to J prime. Don't know if that helps. Then we could try to show J prime BOD. Does J prime lie on this? Oh wait, that's kind of interesting. Oh no, that's not true. Yeah, I don't know if any of that really helps. I'm going to just get rid of that. Can we project onto the circle? If we can prove NHL is similar to AIB1, we're done. Really? Okay. Yeah. IDHC is cyclic. That's a good point. See if anything else lies on that circle. For IDEHC. NL is parallel to AC. If we show B1BC, B1B, and the C angle bisector, and the line through A parallel to BC. That's interesting. So you're saying that this, and this concur. Interesting. Or we want to prove that. If we can prove that, that would solve it. Yeah, how would we show that? Yeah, that is an interesting fact. You just take AI, you take the perpendicular from I to AB, and then you show that DB1, this parallel, and CI are concurrent. All right, you guys want to come back to this one later? There was another problem that I wanted to do. I forgot about.
We can.
Okay. All right.
I mean, in reality, we solve this problem. It is just that we are trying to avoid that computation. But if we just computed that, it will be proved.
It would be solved. Yeah. All right. I'll stick with this a little more because, yeah, I like GeoKing's idea. Seems interesting.
But may I ask why is that sufficient?
Yeah, I'm not sure.
Can you delete D1D and name the intersection of CI with the parallel through A to the BC?
Yeah. Oops. I want it to be a gray point. Call it R. So ARC is isosceles, right? Yeah. Oh, and it looks like, yeah, actually A is the circumcenter of RJC. Oh, using like Menelaus. I wonder if there's a way like using pole and polar or something. Not sure. Yeah. There's this one problem I wanted to do using isogonal conjugates. Yeah, this one. This one looks cool. So we have a triangle with incenter I. So basically we draw the theta angle bisectors. And then we draw, yeah, so I could draw, yeah, I'm not going to draw the end circle, just draw the angle bisectors. And then we draw the perpendiculars to each side at the foot of those angle bisectors. And then that gives us a new triangle. So we have, I'm going to rename stuff later, but basically, so we have this line, and then this line, and this one, and it gives us a new triangle. And then basically, if we draw the 9-point, we want to show that the incenter of the original triangle is the isogonal conjugate of the 9-point center of this new triangle. Let me call this I instead. So let's call this K. I'm going to rename, so this is A1, B1, and C1. So basically, yeah, we draw the 9-point center of GHK, and that's supposed to be the isogonal conjugate of I in triangle GHK. That's what we want to prove. Cosneta point. I didn't know that. The cosneta point is the isogonal conjugate of the 9-point center. What is the cosneta point?
is the isogonal conjugate of 9-point center.
Oh, that's just how it's defined.
Yeah, there's a property, well-known property, that if OA is the circumcenter of OBC, and OB and OC are defined similarly, then cos theta point is the intersection of OA, AOA, BOB, and COC.
Okay. So let me draw N. I don't know if there's a... Do you know which triangle center the 9-point center is? Is it 5 in GeoGebra?
Yeah, it's 5.
Okay. Okay. Okay, just a sec. GHK5. I'll call it N instead of D. Okay, one sec. I'll draw the circumcenter. Okay, so you want me to draw the circumcenter? Call it O. Yeah, they look like isogonal conjugates. So A1, B1, C1 is the pedal circle of I. So we have to show that it's also the pedal circle of N. So let's think about that. Yeah. Guess that's okay. Yeah. So pedal circle of cos theta point. Yeah, I don't know much about it. But yeah, so we're saying N has the same pedal circle. Oh, really? So if we draw the orthocenter, yeah. Maybe, yeah, could we try doing an angle chase?
We don't even need NH, because we just want to prove that GI and GN are isogonal with respect to angles C1, H, B1.
C1H, B1, wait, we don't even need what point?
C1, G, B1.
Okay.
because it will be symmetric.
So we don't need point. What point do we not need?
It can stand, but there's another approach, just to
Okay.
focus on one vertex.
Yeah, we just have to show that those two are isogonal with respect to these. Yeah. Yeah, basically you're saying we don't need H or K, really.
They can be useful, but I don't know. Maybe they're not.
Yeah, I'm gonna hide them for now just for that reason. Whoops. Yeah, so all we really need is this. And N is the center of that circle. And then we want to show that angle C1G. Sorry, I'm going to hide this too. We want to show that angle C1GI is angle B1GN. Let's draw a good picture. Whoops. Yeah, this seems like an easier problem. Oh, but the N, oh, but how did we define N?
Yeah, I forgot about them.
Okay, so yeah, I think, yeah, we do need those. Yeah, this one feels hard to me. Yeah, maybe. So this is the, okay, so if I reflect O over N, I would get the orthocenter.
Can you draw the circle of ABC
Yeah,
and intersect the A1 with circle of ABC and the other ones?
okay. All right, so we have the midpoints of all those arcs.
I guess these lines were drawn, so there are two lines now. It will be hard to disappear the line.
Oh, I'm sorry, what did you say?
You draw the same line twice, so it will be hard to make disappear the line.
Oh. Yeah, I could just,
Okay, this is easier, you're right.
yeah. GKH is homothetic to the excentral triangle.
It's also homothetic to DEF, so that's why I draw DEF.
Okay. Interesting. So yeah, EF is perpendicular to AI. Yeah, they're mutually perpendicular to AI, BI, and CI. So yeah, that makes sense. Sides are all parallel. Yeah, this is hard for me. Let's see. Yeah, how do you use the N as the 9-point center?
Can you draw the ortho center of GHK?
Yeah. Oh, whoops, I think it reflected across I instead of N. There we go. Guess I'll call it, I don't know, Q. Just don't know what letter to use. So yeah, this circle doesn't actually pass through B. It's just in this figure, it's like true, but yeah, there we go. So yeah, we could try to calculate angle NGH and IGK.
Can you draw the circumcenter of ABC?
Okay. Hold on just a second. Of ABC? Oh, you know what? Yeah, there we go.
By homotheity, IJ is parallel to OQ.
Ah, interesting. Okay, so
Both of these are Euler lines.
So IJ is parallel to OQ. Trying to draw the best figure. That looks okay. Yeah, I feel like I need to know more about isogonal conjugates. So I don't know if there's any other special properties they have. So they have the same pedal circle. Like, so I know isogonal conjugates, they have the same pedal circle. They're also obviously isogonal with respect to the three angles, but I don't know if there's any other property it's useful. So if they have the same pedal circle, so I guess one thing we could say is that the midpoint of IN would be the center of that circle. So we could kind of rephrase it if we wanted. We could say, let the center, yeah, we could say let L be the center of A1, B1, C1. And then we could say reflect I over L, and then show that that's the 9-point center of the triangle. So basically, yeah, you're reflecting I over the circumcenter of A1, B1, C1. And you want to show it's the 9-point center of that triangle. That might be a better way to phrase it. I'll be right back, just a sec. All right, thanks for waiting. Let's take another look at this. So yeah, you reflect I over the circumcenter of A1, B1, C1. And then we want to show it's a 9-point center of GKH. And then
if we have an arbitrary triangle, can we like compute compute what is the angle which when you take the 9-point center like N and you have triangle ABC, then like angle NAB or something like that.
Oh, you're saying if N was the 9-point center of ABC?
Yes. Because we can actually compute the internal angles of HGK.
With point I.
HGK, we can compute the internal angles because, like, for example, oh, okay, then I will not say, but
yeah, it's all right. But basically, we know that these are both right angles, and so that kind of makes it easy because it's not hard to yeah.
Of course, the angle C1B1B that is not easy to compute, and in fact, I don't think we can like straight compute it without like using trigonometric functions.
Yeah. Yeah, I think it might be hard to compute the angle between the 9-point center because we know the angle between point O and we know the angles between point H. But
then we have the midpoint, which is not good for angles.
Yeah.
But maybe we can show that those angles are equal somehow, like with using, I don't know, trigonometry. Maybe.
Yeah. Yeah, it could be. Yeah, I'm not sure. Could work. Yeah, so we would need KGI and HGN. So really, like LQ is like a mid segment. Well, let's see. So N, this is kind of interesting because N is the midpoint of OQ and L is a midpoint of IN, right? So it's the midpoint of one thing and it's the end point of the midpoint of this. Wonder how we use that. Are A, L, and J collinear? I don't think so. Oh, it almost wait, maybe A, L, and J are collinear. No, because by symmetry, then the others would have to be. Okay. need config information. Okay. Do you want to move on to the next problem? The others are I3435, so probably somewhere in between this and the easier ones. Okay. All right. Oops, sorry. I think we might have done this before. I don't remember. But yeah, if you participate